Hey everyone, I'm Andrei Pangin, the lead software engineer at Одноклассники, one of the largest social networks in the world, and probably the largest one running Java. My today's talk is not about just random facts. I will discuss problems that arise at Одноклассники as well as all other projects all around the world. I often hear Java developers asking about heap dumps and stack traces. This today's talk is inspired by the questions asked on Stack Overflow. This is just a small portion of them answered by myself. So I guess I shouldn't explain what stack trace is. Every Java developer saw it when he or she makes the very first mistake. So let's go directly to the demo. Here is a small program with a method that checks if an array is sorted or not. I run this method many times in the loop, but I made a typical off by one mistake here. I forgot -1. So what will I get there? Right. Array index out of bounds exception. But what the hell? Why I see the exceptions without a stack trace? Here, in the exception handler, I call print stack trace, but where is my stack trace? Who knows? Okay, let's see. Let's run this the same example with the following option. It's a JVM flag, mid stack trace and fast throw. Here are the exceptions again, and yeah, here are all our stack traces. There is an optimization in HotSpot JVM that doesn't generate an exception stack traces for implicit exceptions thrown from a hot code. The same applies not only to array index out of bounds exception, but for other implicit exceptions as well, like null pointer exception, arithmetic exception, and so on. If such an optimization exists, there must be a reason for that, right? Maybe it makes the performance faster. Let's see. Here's a primitive benchmark I wrote to measure the cost of creating a simple object like Java util date with the exception object. I use a JMH micro-benchmarking framework. It helps to avoid common benchmarking pitfalls like warm-up, JIT optimizations, and so on. Look, it takes just 8 nanoseconds to create a simple object, but 150 times more to create an exception. Other exceptions are really expensive. Why? In fact, it's not exception creation that takes time, but rather collecting a stack trace. Each constructor of an exception calls fill-in stack trace method, which in turn results in a native method call. But good news is that this method is not final and it is public, so we basically can override it. So let's run our benchmark with an empty fill-in stack trace. Yeah, now we see that exception is as fast to create as a simple object. There is also another way to create fast to instantiate exceptions. There is a special protected constructor which accepts additional arguments. If we set writable stack trace to false, then exceptions will be again fast to create. Good. Now we know that. Now we know the exceptions, the cost of exception creation. Let's measure the cost of catch, throw, and catch. This benchmark calls some method recursively, and at the given depth, it throws an exception. Here are several interesting outcomes from the benchmark scores. First, we see that with just one method call, the try catch basically costs nothing. It is explained by the fact that HotSpot JVM can inline one recursive method call, and if the catch clause is in the same context as throw, then throw will be as fast as the simple goTo. The second interesting fact that on a deeper levels, the cost of throw catch is roughly proportional to the stack depth, which is quite understandable because it takes linear time to find an exception handler and to work the stack trace. Let's go on with exception measurements. Filling stack trace just collects stack trace in some internal representation. But in order to print the stack trace or to send it somewhere, we need to convert it to a Java representation, an array of stack trace elements. So let's the measure get stack trace call. Wow, it appears to be more than 10 times slower. So not only the collecting stack trace takes time, but also converting it to a Java representation. Why it is so slow? Let's look into Gdp Source Code. Here's the implementation of getStackTrace method. And we see here loop, and for every frame, there is a native method call, which results in a stack trace element object creation with a number of fields there. Note, there will be even more fields in stack trace element in Java 9 related to modules. And here is a surprise for those who parses traces with regular expressions or so on. Be prepared that your parser will be broken because the format has changed in Java 9. What we've seen is that exceptions themselves are just regular objects. What takes time is collecting an exception stack trace. And this time is linear depending on the stack depth. Throw is also cheap if the catch, if the exception is caught in the same context. Note that the context can include several methods due to inlining. Otherwise, throw performance also depends linearly on the stack depth. And a few recommendations on how to use stack traces. First of all, turn off this ugly JVM optimization. It will really help you in production to debug weird null pointer exceptions and so on. It is usually a bad practice to use exceptions for a normal control flow. However, in some rare cases, it can really help. For example, in a visitor pattern, when you want to return from a loop which in outer method. And in this case, prefer no stack trace exception with no stack traces. That's all about exceptions. In what other cases do you need stack traces? Your variance? Well, the basic use of stack traces is to see what an application is doing. jstack utility can dump all threads with their stacks and basic information about thread, like thread name, priority, and so on. What is interesting here is an ID. It is the native thread ID given by the operating system. For example, if you see top utility to find which thread takes the most CPU time, then you may match the top output with thread dump by this NID. We also see in this thread dump that thread 1 is waiting for some reentrant lock, but there is no clue which thread holds this lock. However, there is a less known JVM option that allows you to print this information. Here additional lines appeared saying that thread 2 holds this lock. You may be interested why this option is not enabled by default then. Well, for each reentrant lock, HotSpot knows which thread is assigned to this lock, but there is no the reverse mapping. So in order to find all the locked reentrant locks, HotSpot needs to traverse the whole Java heap to find all such locks. And of course, this takes time. Okay, another popular case that relies on exception stack traces is logging. Imagine an application that prints some warning message. This message can be actually printed from anywhere in the code, but you want to know from which place this message is printed exactly, preferably the file name and line number. In C language, there are preprocessor markers, file and line, but there is no such markers in Java. The only way you can achieve this information is by looking at the stack trace. So this is typical solution how logging frameworks get the location information. But as we know, the get stack trace call can be really expensive. Is there a better way? One may think that threads get stack trace can be faster because it doesn't need to create an exception. Who thinks it is faster? Or maybe slower? The same? Yeah, actually there is no magic. Threads get stack trace method also creates an exception. However, there is a secret method to get this location information faster. There is an interesting class named shared secrets in JDK, and it can access not the whole stack trace, but the particular stack trace element from this exception stack trace. So we don't need to convert all stack trace elements, just the element we need. The bad news is this won't work in future versions of Java, because the all stack working mechanism was completely rewritten in Java 9. That's the usual thing that happens with private APIs, so don't rely on private APIs unless you have a backup plan. Besides logging, there are other cases where method behavior may differ depending on who calls this method. For example, class for name may find the class or throw class not found exception depending on the class loader on the callers class loader. The same is true for getting resources or loading libraries. Access control deprivileged method may succeed or fail depending on whether it is called by trusted or untrusted code. If you are to write caller sensitive method by yourself, how do you know the caller? The only way to know it, again, by obtaining a stack trace. However, there is a faster method. Note that it is also in undocumented private API. But this API will be still there in Java 9 because there is already a lot of code, production code that relies on this call. So it was decided to leave this method in Java 9. However, it will be likely removed in Java 10 or so. Okay, we've seen a number of use cases where standard stack working API doesn't work. Ideally, there should be a completely new API that allows to work only a limited number of frames, for example, top 10 or so, to find frames only matched to the given criteria. The information should be obtained lazily. For example, if you don't require file name and line number, why spend time getting it? To meet these requirements, Java community came up with a brand new API in Java 9. And it is already known that it will be a part of the standard. This API is called Stack Worker, and it's really powerful, just like another known worker. At the same time, this API is quite simple. Just call this method to get an instance of Stack Worker. There are a few options to modify the default behavior. I will talk about these options a bit later. And another overridden version that is optimized for the given stack depth. Okay, what can we do with a Stack Worker? We can basically iterate through all frames and, for example, print them. If you add show reflect frames option, then a few more methods will appear in the stack trace, methods related to reflective method invocation. Another option, show hidden frames, yields yet more detailed stack trace. Show hidden frames also implies show reflect frames. And here is the central method of this new API. A scary signature, right? With lots of generics. But it's rather easy to use. Inside work method, there is a stream, and this is just a regular stream of stack frames, and you may use it whatever you may do whatever you want with it. Skip frames, filter them, map, and whatever you can do with a regular stream. For example, if you need caller stack frame, you can do things like this, but there is also a shortcut method to get a caller class. Note retain class reference option. Without it, you'll be able to access just a caller class name, but not the class object. Here's a bit more complicated example. Here we get top 10 frames whose caller belongs to org Apache package. But why the signature is so tricky? Why not just a method that returns a stream of frames? Any ideas? Okay, imagine that API just returns a stream of frames. We can pass this stream to some another thread, forget it, and after several hours invoke methods on this stream when the original stack trace is no more and original thread is already dead. Of course, the key point of the original API design, the laziness of its method, will no longer work. So the key idea of this tricky signature is to make your work with the stream inside a work method, while the original stack trace is frozen. So you basically can get information from this stack trace lazily. And here is a bonus for you. No one from Oracle will tell you about this API because it is non-public, undocumented. It makes possibly not only get classes and methods from a stack trace, but also local variables, info, monitors, and even expression stack. Let's see an example. Okay. Here's a labyrinth program which searches an exit from a square labyrinth using a recursive method. When it finds the exit, it dumps the current stack. It starts with the cell 99 and tries to get to a cell 00. Let's run it. Okay, if we use a regular dump stack method, then of course we get a stack trace with the same methods. Of course, it is a recursive method. But if we change it with our stack trace dumper, which uses live stack frames, you'll be able to get the values of local variables at each method call. And here you can trace the whole path to the labyrinth exit. Here's how this stack dumper looks like. It gets a stack worker from the live stack frame method, from the live stack frame interface, sorry. And for each frame, it prints the frame itself and the locals, which we get using getLocals method. Note that all the methods are called using reflection because the interface is package private and we can't access it directly from our application. The other bad news is that we can't use actually reflection on a system classes in Java 9 unless we explicitly add this ability using the JVM option it opens. Okay, we can't talk about stack traces and not mention recursion. Let's have some fun with the recursion. What will happen if I run this program? Stack overflow error, right? But how much frames can I construct before I get stack overflow error? Hundreds, thousands, millions? Well, let's measure. So we catch stack overflow error and print the depth. 24,000, 30,000. 24 again. Each time the number of frames is different. 23, it can differ significantly. What can be the reason of this difference? Any ideas? Okay. Yeah, that's how recursion looks like. The clue is the background JIT compilation. Originally, the execution of methods started in interpreter, but after a certain number of invocations, the JIT kicks in and start compiling, but it compiles in background thread. And while compilation is working, the execution continues in interpreter. And as soon as compilation finishes, the next invocation switches to compiled version. Since JDK 8, when tiered compilation is enabled by default, there are even two compilers in HotSpot JVM, C1 and C2. And of course, compiled methods are use less space on stack because they don't require they're not required to put everything on stack. For example, they can cache some local variables in registers. C2 compiler is even more optimizing, so its stack frame is yet smaller. And due to concurrency issues, there can be different number of interpreted and compiled frames each run. And that's why the number of recursive calls is different. I ran this test with the default stack size, which is 1 megabyte on 64-bit platform. Of course, the larger the stack size is, the more calls I can do. There are JVM options to modify the default stack size, and not everyone knows that there is a thread constructor that can change the stack size of an individual thread. But why on earth care about stack sizes? For bloody enterprise applications, of course. You see here just a single line of business logic, and everything else is boilerplate of frameworks, frameworks, frameworks. The last but not the least use case of stack traces is profiling. The idea of sampling profiler is very simple. The profiler wakes up every small period of time and collects stack traces to see what application threads are doing. And this is a really lightweight approach, so it is suitable for production. Let's see how it works. Here is a demo that I want to benchmark. It does many things. First, it generates some random points. Then it calculates distance from this point to some another location. And finally puts this distance to a map. From the first sight, it's not obvious which will take the most time. It can be location generation, it can be mathematics, and it can be distance, a hash map operation. So let's measure using a standard benchmark, standard profiler, which comes with regular GTK package, Visual VM. Hey, where are you? It can't find my application. Okay. Let me try again. Yeah, here it is. Choose sampler, CPU, let it work for some time. And what I see in a sampling profiler that almost 100% time is used by system identity hashcode method. This doesn't look true for me. I don't think that almost everything is used by system identity hashcode. Why the profiler can lie? The problems originate from JVM's method of collecting thread dumps. HotSpot JVM cannot get stack traces at any arbitrary point. It can collect stack traces only at known positions in the code known as save points. Usually the save points are located at the ends of the loop and at method exits. The other problem is that JVM cannot distinguish a native method that is blocked on some system call from a method which actually does some work, because all threads are measured equally. This is not a problem of a particular profiler. Many other popular profilers also suffer from the same problem. But HotSpot JVM has an undocumented API. Yeah, it has a lot of undocumented APIs, which can take thread stacks not only at save points, but almost at any time. So the idea of using this API is simple. We catch timer signals from operating system and call this method to collect the stack trace of a thread that is running. And originally this API was invented especially for Oracle Service Studio to give it competitor advantages maybe. But since HotSpot sources are open, we can also use this. People noticed such a treasure, and so did I, and implemented this approach in my async profiler project. And here how the output of async profiler looks for the same example. You know that, see that system identity hash code is somewhere in the bottom, and what takes the most time is actually a maths function. As a bonus, this profiler shows not only Java code, but the native code as well. Now when we know the benefits of stack traces, let's see how to get them efficiently. We can dump threads right from the same JVM using convenient Java API, which returns a stack trace in Java representation. For a more compact representation, there is another function provided by JVM tool interface. It returns an array of JMethod IDs. If any one of you has ever written some JNI code, then you know what JMethod ID is. This is also a much faster way to get stack traces. If you wish to get stack traces of a different process, then the fastest way is to ask virtual machine to dump the stack traces by itself. You need just to send a quit signal to it using kill -3 or so on. And JVM will execute the command by itself, and it doesn't create any Java objects or intermediate structures. It just walks through all threads and prints them to standard output. The same can be achieved by jstack utility, but the output will be redirected to the jstack console. You might know that jstack has a special forced mode. Though the output looks similar, actually these are two completely different utilities, and they involve completely different mechanisms. Let's see. jstack without f involves a dynamic attach mechanism, which works as follows. jstack creates a special file at the current directory with the process ID of the target JVM and sends a signal to the JVM. JVM catches this signal and in response to it starts attached listener thread and creates a Unix domain socket to communicate with jstack. Then jstack utility sends a command through this Unix domain socket, and JVM executes these commands and sends output back to the socket. The benefit of this approach is that the commands are executed by JVM itself at the maximum possible speed. But in order for this to work, JVM must be alive and healthy. And JVM also verifies that the credentials of the attaching process are the same as the credentials of the JVM process. So you cannot use this mechanism to dump a JVM launched by another user, even if you run it under root. And how jstack-f works. It's a completely different mechanism that relies on Serviceability Agent. First of all, it doesn't require any cooperation from JVM. It just sends stop signal to completely suspend the JVM process. And then it uses operation system debugging facilities to read data from the memory of the remote process. And then jstack reconstructs the VM structures and walks through the reconstructed stack. A good thing is that it requires no cooperation from JVM, and it can work on a hunk or busy or otherwise not responding process. As a bonus, it can dump not only Java frames but native frames as well. But since it requires reading from the remote process, it can be really slow. And it can work only on the same version of JVM because it should know exactly the layout of all VM structures. Okay, that's all about stack traces. Heap dump is another essential instrument to analyze problems like memory leaks. I guess you're already familiar with jmap, the main tool to create heap dumps. Here is how a command to dump all live objects to a given file name looks like. There is a number of tools to analyze heap dumps, like Visual VM, Eclipse Memory Analyzer, and so on. I hope you're familiar with at least one of them, so I won't talk about it anymore. However, dumping heap is usually a rather slow process and can be used in production systems often. But in order to analyze some memory leaks, you not always need to dump the whole Java heap. Sometimes just plain histogram would be enough. The histogram shows you which class takes the most amount of bytes allocated in heap. jmap, like jstack, also has two modes, regular and forced. And they also use dynamic attach and serviceability agent. So the benefits and drawbacks are roughly the same. Jmap without -f asks the VM to make the heap dump, and this is really fast. But this works only on a live JVM. Jmap -f can analyze hung processes and can even analyze core dumps of dead processes. But it requires the same version of JDK, and this can be 10 to 100 times slower. So the force mode is not really good for production environments. But there is a trick to make heap dumps faster, even in forced mode in production. The trick is that you don't do a heap dump, but rather a complete core dump. Core dump is not a heap dump. You can create a dump of the whole process in operating system using GDB or gcore. But jmap can extract a heap dump from a core dump using this option. This also takes time, but this second command can be done in offline. So the idea is that the core dump is generated as fast as your hard disk can write. And then application continues to run, and then you can make a heap dump while the application is already working. The same can work on Windows as well, but instead GDB, there is another tool to generate core dumps. While you can always create heap dumps manually using jmap, sometimes it is good to make a JVM dump heap automatically. The typical case is out-of-memory error. Another useful case is garbage collection, full garbage collection. For example, if you have a low latency application, then you usually don't want a full GC to ever happen, because it can take several seconds. And there are JVM options to automatically generate heap dumps in such cases. By default, the heap dumps are generated in the current directory, but you can override this with a special JVM option. After an out-of-memory condition, an application is not guaranteed to work correctly. The best you can do in a production environment is to let JVM make a heap dump and restart it as soon as possible. A special JVM flex appeared in Java 8 update 92 to do this. However, these options are not really useful because it was possible even in earlier JDKs using on out-of-memory error flag. What if we decide to dump heap not only on out-of-memory error, but in some other cases? You can do it yourself. To dump heap from within application, you can use again HotSpot private API. But a better way, and good news is that it is a standard way, which is supported not only in HotSpot but in other JVMs as well, is the JVM tool interface, which can iterate over heap. Using this method, you can iterate on not all classes, but if you need just to traverse some objects of some given class, for example, you want to find only strings in your application. Then you can iterate only over strings. And this is done in 2 steps. The first just tags the objects of the given class, and the second call get objects with tags returns an array of j objects. And you can do the same for an external JVM using Serviceability Agent. Serviceability Agent is actually a separate big topic. I don't really want to spend much time on it. Just want to show one example. Imagine that you are a hacker and you want to steal private keys from a running Tomcat server. And so you can use such program to find all private key instances in the running JVM and dump it. To use the Serviceability Agent, you should include SAGDI jar in the class part of your application. This is almost everything I wanted to tell you today. In the conclusion, I would like to suggest to use heap dumps and thread dumps in production. And there are a number of ways to do this, both from inside a JVM and from external applications. And I will be glad to continue discussion today, anytime later. Just drop me an email, follow me on Twitter, or ask me today. Thank you. Thank you. Thank you. Thank you. Thank you.